Okay, kids, we're back at it today, and new concept as we move forward into the next section of the textbook. And we're going to be talking about the law of conservation of energy. And basically, this is a very useful law that allows us to study the motion of objects using energy instead of kinematics equations, and the concept of kinetic energy and the concept of gravitational potential energy. So that's what we have written here in green. The motion of objects can be studied by using kinetic energy and gravitational potential energy. What we're going to introduce to you right now is a new energy, and it is an energy that's an addition. It's a sum. And what we get when we add kinetic energy and gravitational potential energy, so as I have written here, the sum of kinetic energy plus gravitational potential energy is called the total mechanical energy. Total mechanical energy, and that is E with a subscript P. E with a subscript T. So I'm going to rewrite this sentence that's in English. I'm going to rewrite it in a language known as math. Here's an equation. ET is equal to EG plus EK. Or let me rephrase that for you. The total mechanical energy of an object is equal to its gravitational potential energy plus its kinetic energy. This is very, very useful when that is an object that is moving through the gravitational field of the earth. Maybe you've thrown an object up into the air and it falls back down, or maybe you've dropped an object. This is a very useful law that helps us study that motion without using kinematics equations and dynamics equations and all the vectors that are associated with it. So that's the power of this new equation right here. Now, that's the energy part of today's title, the law of conservation of energy. I've told you what energies are involved. I've told you that we can add up these two energies, gravitational and kinetic, and come up with this new energy, which is a sum, a total mechanical energy. That's the energy part. Now we want to look at the conservation part of this law. And it says that during an object's motion, total energy is constant. It is conserved. It doesn't change. That means the change in total energy is zero. Or another way of writing it is, let's break down what delta means. Remember what delta means? It would be change in total energy. So that means total energy final minus total energy initial. That has to equal zero. That's what the delta means. Or another way of writing this out, and a very powerful way of writing this out, is we take total energy initial, we bring it to the other side, it becomes positive, and we have this very powerful equation, almost a method for studying objects that are dropped or thrown into the air, that total energy final is equal to total energy initial. And when we use this equation, we assume there's no friction or resistance forces like air resistance or anything like that. We're going to assume that they are non-existent or so very, very, very small. Now, let's see here. Probably the best way to really understand the power of this equation and the power of the equation for gravitational potential energy and the power of the equation for kinetic energy, all three of these equations together, is through an example. So why don't we do an example? So here's the situation. Here is an object. Right here, there's the object. And we're going to drop it. So it could be a ball that's being dropped, what have you. And we're going to assume that the initial velocity, initial speed of this object is zero, meaning it is dropped. It's not thrown up into the air. It's not thrown down. It's dropped. Drop the mic. Okay. And its mass is 0.5 kilograms. So what we're going to do is we are going to calculate the gravitational potential energy initial, which would be the mass, 0.5 kilograms, g, without a vector sign, there's no negative here, Negative is not here, so it's just 9.8 newtons per kilogram. This is all scalar times the height, and we're going to say that the height initial is 0.75 meters. So if you multiply 0.5 kilograms times 9.8 newtons per kilogram times 0.75 meters, you will find that the initial gravitational potential energy here is 3.7 joules. Try that for yourself. You can pause the video. The other thing we can calculate right here is the kinetic energy initial. That's an ugly K, but it had to be done. Okay, and it is equal to the equation for kinetic energy, half the mass times the speed it has at this point. Well, it's being dropped. It has no speed at this point. So therefore, it has no kinetic energy, 0 joules. Then we can calculate the total energy initial. The total energy initial. And the total energy initial is equal to the gravitational potential energy it has at this point plus the kinetic energy it has at this point. And we add that up, and that's 3.7 plus 0, or 3.7 joules. So that's how much energy it has at this point here. Then we drop it, and we let it drop. So now it's here. So now let's say that its new height, or what I'm going to call height in the second situation, okay, is equal to 0.5 meters. Well, here's the power of this situation being referenced back to the law of conservation of energy. The total energy that it has when it's at height 2, 0.5 meters, let's call that total energy 2, is equal to the total energy it had here when it was at this height, height initial, which is total energy initial. It's still 3.7 joules. Whatever energy it had here, total energy, is the same as the total energy it has right there. It hasn't changed. It has not changed. What we can now do is calculate what is the energy, gravitational potential energy, at this point. It's no longer 0.75 meters in the air. It is 0.5 meters in the air. So I can actually calculate the total energy, the gravitational potential energy of this object at the 0.5 meter spot. That's 0.5 meters. So it is 0.5 kilograms. Just put kilograms there. 0.5 kilograms right there times 9.8 newtons per kilogram. It's a scalar, no negative here. You don't see a vector sign over the G, times the new height, 0.5 meters. And we now have that the gravitational potential energy of this object at this height number 2 is 2.4 joules. That's how much energy it has here. All right. Next, we can use this equation right here. Let me rewrite it for you. That total energy is equal to kinetic energy plus gravitational potential energy. We can use this equation right here to calculate what the kinetic energy of the object is right here, because it's falling right here. It's got a certain velocity. It's moving downward. So it's going to have motion. It's going to have kinetic energy. Didn't have any kinetic energy here, but it does here. So all we have to do is rearrange that equation, right? Bring the EG over to the other side, and therefore it becomes negative, right? And we now have an equation that will let us calculate the kinetic energy. Kinetic energy is equal to the total energy minus the gravitational potential energy. And that's what I have right here for this particular situation, for situation 2. Kinetic energy 2 is equal to total energy 2, which never changes, minus gravitational potential energy 2. Well, we know that the total energy is always 3.7 joules. We just calculated that the gravitational potential energy when it has this new height of 0.5 meters is 2.4 joules. So 3.7 joules minus 2.4 joules leaves 1.3 joules. That means the kinetic energy of this object when it is at this new height of 0.5 meters is 1.3 joules. Think about that a little bit. Pause the video, think about it a little bit, okay? So we know the kinetic energy of the object here, 1.3 joules. So let's write out an equation for the kinetic energy of this object when it is at this position, height 2. All right, it's fallen a little bit. It used to be at a height of 0.75 meters. Now it is at this new height, height 2 of 0.5 meters above the ground. So it's falling. So here we go. Kinetic energy in the second situation, EK2, is equal to half the mass of the object times velocity 2, or speed 2, speed at this second situation, right, squared. So what I'm going to do is I'm going to rearrange this equation. So I'm going to multiply both sides by 2. So this becomes 2 times kinetic energy in the second situation, 2 times EK2. The 2 times the half leaves me a 1, so I don't write that down. And I have mass times speed 2, speed in the second situation, squared. What I'm now going to do is divide each side by m. So I divide this side by m, and I have 2 times kinetic energy in the second situation divided by m. If I divide this side by m, I'm just left with speed in the second situation squared. And now what I'm going to do is square root both sides. So I can square root both sides and I get the square root. So this is a square root of everything. All right, everything in here. So it's 2 times the kinetic energy in the second situation, and we know that that's 1.3 joules. We know that. Divided by the mass. We know the mass is 0.5 kilograms. So in your calculator, you would go 2 times 1.3, press equal sign, then divide by 0.5, press equal sign, then square root, press equal sign, and you will have the speed of this object when it is at position 2, a height of 0.5 meters. So right here, here's the calculation I described. 2 times 1.3 joules, the kinetic energy it has at this height, divided by 0.5 kilograms, leaves us with this, square root of 5.2. So it has a speed at position 2, or speed 2, see, of 2.3 meters per second. So what I want you to do now is find out how fast this object is moving when it is at height 3, the ground. When it's just about to hit the ground, what would its speed be? We'll call that speed 3, V3. When it is at a height of 0 meters, when it just touches the ground, how fast is it moving? Now, some of you may think, well, it hit the ground, the speed is 0. No. If that were true, anytime you drop something, it would never break. How fast is it moving as it hits the ground, as it just engages with the ground? So what I want you to do is review the method that we just went through right here for calculating speed at the second height. Use this method to find out what its speed is when it just hits the ground. Pause the video and try to figure it out on your own. Once you've tried it, restart the video and we'll pick up from there. Okay, well, I hope you listened to my advice. So let's recap. We're interested in the speed of the object just as it hits the ground. This is what we have learned from the law of conservation of energy, that the total energy of the object just as it hits the ground, or the total energy of the object at position 3, is equal to the total energy of the object at position 2, which we just calculated, and it's also equal to the total energy of the object at position 1, just as it was dropped, and that is 3.7 joules. That never changes during the entire motion of the object as it is dropped. The law of conservation of energy. That's what makes this method so powerful. Well, total energy in the third position is equal to the gravitational potential energy of the object, third position, plus the kinetic energy of the object, third position. Well, look, gravitational potential energy in the third position would equal the mass, half a kilogram, times the magnitude of the gravitational field strength near the surface of the Earth, 9.8 newtons per kilogram. It's a scalar here, okay, no negative sign. Well, height 3 is 0. It's just hit the ground. So that means that the gravitational potential energy in position 3 is 0 joules. It has none. All the energy is kinetic. And we can prove it by remembering that total energy is equal to kinetic energy in the third position plus gravitational potential energy in the third position. I'm going to bring gravitational potential energy in the third position over to this side. I'm bringing this over and it becomes negative. So now my equation is kinetic energy in the third position is equal to total energy minus gravitational potential energy in the third position, which is 3.7 joules minus 0, or the kinetic energy in the third position is 3.7 joules. All of the energy is kinetic. All of it. All of that initial energy, which was potential energy when it was being held, just as it was dropped, it was 3.7 joules. Of all of it was potential energy. Now it's been dropped. It's just hitting the ground. So all of this energy is kinetic. There you have it. All right. So now I can write out the equation. Kinetic energy in the third position is equal to half the mass times the velocity, the speed in the third position squared. There's the equation for kinetic energy. I'm going to go through the same rearranging I did before. Multiply each side by 2, divide each side by m, find the square root, and the square root is over all of it. Okay, the square root is over numerator and denominator. I plug in the numbers. In my calculator, I would type in 2 times 3.7 equal sign, divided by 0.5 equal sign, square root that equal sign, and I get 3.8 meters per second. This is a speed. There's no vector here. All right. That's why I know it's falling downwards. I get it. The velocity would be negative 3.8 meters per second, but we only calculate speed here. Energies are based upon scalars. And it makes a lot of sense that it's larger than the speed it had when it was still in the midst of its drop. Position 2, its speed was 2.3 meters per second. As it's just about to hit the ground, it's 3.8 meters per second. That makes sense because, as we know, things are accelerated as they fall downward. All right, let's try another example. This is the roller coaster. And the roller coaster goes through this blue path here. All right, and the roller coaster car is red here. And when it's right here, it's at a height of 50 meters above my height zero line. So it's at a height of 50 meters above my height zero line. And when it's right at this spot here, it has a speed of 2.0 meters per second. And we're going to call this situation 1. So that's height 1, speed 1. And it goes through the path here, zoom, 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 gets up to here. And when it's at this spot right here, it has a new height. This is position number 2. So we're going to call this height 2. When it's right here, it's at a height of 20 meters. What we want to find is, what is the speed of the roller coaster when it is 20 meters above the ground? What is speed 2? Question mark. We need to calculate that. Now, the interesting thing about this is I've not told you the mass of the roller coaster car, and I won't. It will not be given to you. All right, not given. How do we solve this? Well, we solve this by using the law of conservation of energy, that we have a total energy at position 1 and a total energy at position 2, and that total energy 1 is equal to total energy 2. The law of conservation of energy. That is how we're going to solve this. So let's proceed with the solution. And let's get a few things straight right up front. We're going to focus on what's in the black here. Total energy of an object is always equal to its gravitational potential energy plus the kinetic energy. And I'm reminding you that the equation for gravitational potential energy is mgh, mass of the object times the magnitude of the gravitational field strength near the surface of the Earth times whatever height the object has. I'm now going to remind you that the kinetic energy of an object is equal to the mass of that object times its speed squared, all divided by 2. Or if you don't like it like that, you can have half m, that's a horrible m v squared. They're equivalent. Dividing by 2 or multiplying by a half is the same thing. Let's start the solution. Total energy in the second situation is equal to total energy in the first situation. There, I've written the law of conservation of energy. Now, total energy 1 is equal to gravitational potential energy 1 plus kinetic energy 1. And that has to equal gravitational energy 2 plus kinetic energy 2. So all I've done here is realize that the total energy has to be this sum. So I've expanded this to realize that total energy at any situation is always the sum of gravitational energy plus kinetic energy. Total energy is always the sum of gravitational energy plus kinetic energy at any point. So I've expanded that out. Next, I'm now going to write out the equations for each of these. That's why I reviewed them just a few moments ago right here. I'm going to write out the equations. So there we have it. I'm writing out the equation for gravitational potential energy at height 1. I'm writing out the equation for kinetic energy of the object at height 1. Right? These are all ones, height 1, speed 1. Over here, I'm writing out the equation for the gravitational potential energy of the object at height 2. And over here, I'm writing out the equation for the kinetic energy of the object at height 2 when it has a speed v2, and that's what we want to solve for. I'm going to plug in all the information that I know. There you have it. And I'm going to plug in all the information I know. There it is, all in black for you. That's all the data I know. Then I'm left with an m. I'm going to multiply the 9.8 times the 50, gives me 490. I still have an m here. I'm going to square the 2, gives me a 4. I still have a 2 in the denominator. Let's go over to the other side. I have my m still, because I don't know what m is. Remember that? Don't know what the mass is. No idea. I'm going to multiply the 9.8 times 20, gives me a 196. All right. And I don't know the mass. I don't know speed, second situation, and I have a 2 here. So I leave it. What's the next thing we're going to do? Well, we're going to multiply everything, both sides, by 2, and we're going to divide both sides by m. So that means I'm multiplying this side by 2. So this becomes 2 times m490. This becomes 2 times this term. But there's a 2 in the denominator, so it's gone. And I'm just left with m times 4. Similarly over here, look, it's m times 196. I'm multiplying it by 2, so it becomes 2 times m196. Over here, I'm multiplying this term by 2, but there's a 2 in the denominator, so they cancel out, and I'm just left with m speed second situation squared. Now remember, the other thing we're doing is we're dividing both sides by m. So I'm dividing this side by m, and I'm dividing this side by m. Well, look what happens. The m cancels out of this term. Cancels out. So I'm just left with 2 times 490. The m cancels out of this term. So I'm just left with a 4. The m cancels out of this term. So I'm just left with 2 times 196. The m cancels out of this term. And I'm just left with speed in the second situation squared. I didn't need to know the m. The mass cancels. That's kind of cool. Now we've got some algebra to finish, some multiplying. Multiply this, add the 4, multiply this, get 392, okay? Then I'm going to bring this 392 over to the other side. Gives me 592. Try it with your calculator. The square root, and I get the speed is 24 meters per second. So we calculated the speed there by using energy methods. We didn't use dynamics, we didn't use kinematics, we used energy methods, and we found the speed. That's the power of the law of conservation of energy. Now, what I've written for you here in red is some kids like to do this all with algebra and come up with a beautiful expression instead of substituting the numbers in early. Okay, I'll let you follow that all on your own. Just go step by step by step by step and follow the algebra, and you'll come up with an algebraic equation expression for the speed in the second situation, and there it is. Okay, I'll let you look after that. So, we're having a long weekend coming up. If you've done your work and you're all caught up, relax. If you haven't, look at it as some time to get caught up. Because what the principal told me is school is still in. We need to work every day. School is in. We're just not in a building, but school is in. Thank you for handing in your assignment. Some of you haven't done that. You need to do that. Hand in your work. Log in every school day. Take care. We'll see you next time. Bye bye.